I want to spend a little bit of time introducing the idea of pitch stability, and then we'll break up into our groups for the final design meeting. Get you guys together talking about your project. So there's a whole bunch of different kinds of stability criteria that we'll look at in 514 when you take that class. But the major feature is something called pitch stability. And this is the stability. I usually do this later on in the class, closer to the design project, but you guys are doing that early. So I want to give you the information on this because where you set your CG according to the formula related to your airplane determines whether it's stable or not. So I want to give you enough information so that you know how to change your airplane if it doesn't turn out to be stable in X-plane. And there's two features to this. There's the trim, the pitch trim problem, and then there's the pitch stability. So every time you talk about stability, there will be an equilibrium or a steady state or a trim condition. And then from that, there will be a disturbance. And you want to know, well, how does the airplane respond to a disturbance? So the classical pictures that people draw for stability, really simple, is a marble in a bowl. So here's the marble, and it's at an equilibrium. At the bottom. And if you disturb it, what's it going to do? It's going to return. But a key feature of stability is what's called static stability. It's not the motion. It's even before the motion. It's are there forces or moments generated to direct in the direction to return it to stability, to equilibrium. And there are, because if you look at the forces on this, there's gravity down, and there's a normal force out, right? Well, the normal force is not going to return it to equilibrium, but there is a component of the gravity tangential that's going to pull it back. And so that's why it has a tendency to go back. So static stability is defined to be in response, there's a disturbance from equilibrium. And forces or moments, in this case it's a force, are generated to return to equilibrium. So that's the key. You have the equilibrium, you get a disturbance, and then forces and moments are generated. So that happens here. Whereas if we look at a different kind of bowl, like bowl facing upward, this is an equilibrium if we get it right on the top, right? It will stay there if it's perfectly on the top. But if there's any kind of disturbance, then gravity has a component to push it away from equilibrium. So this is stable. And this is unstable. So what's this? with the ball on a flat surface. Will it stay there? Yeah. What if we disturb it over to here? Are there any forces generated to push it back to that initial? No. So this is the in-between case, and this is called marginally stable or neutrally stable. Which really means it's on the borderline between stable and unstable. All right, so when we talk about an airplane and pitching, we have the same kind of features. We have an equilibrium, and it's called pitch trim. So we need to talk about that. So I'm going to draw a real simple airplane to illustrate this. It's just going to have a wing. So the wing has an aerodynamic center. Well, we talked about that's where we draw the forces and moments, just like the airfoil. And so the lift is acting here, of course, perpendicular to V infinity. But if we look at the charts for airfoils, if we make wings out of airfoils, you'll see that some of them, especially a non-symmetrical airfoil, has a negative, a nose-down pitching moment. It's just from the airflow around it. So we're going to say this is in fact, let's draw it more non-symmetrical so that it looks like that. So it has a nose-down pitching moment. And you can see that from the airfoils. Open up to any one of those non-symmetrical, unsymmetrical airfoils, and the pitching moment plot is below the zero axis. It's negative. So to get pitch trim, we've got to have a balance in the moments. In other words, the total moment about the CG has to be zero. Otherwise, the plane will start to rotate up or down. So how do we get that? This thing is nose down. Where's the CG? Because we said the moment's about the CG. Well, if you put the CG back here and you do the distance just right, the nose up moment, the lift times that moment arm, exactly balances the pitch down moment of the airfoil, and you're all good. So you could have the total moment, the negative moment plus the lift times that distance, and if it's zero, then you have pitch trim, because the airplane won't rotate up or down because it's all balanced out. Just like if you have like a seesaw or a teeter-totter, right? If you have equal weights, equidistant, then the net moment is zero, and it doesn't rotate, it doesn't tip. So this is our equilibrium condition for pitch trim. So far, so good, right? Now, what's the disturbance? Well, the disturbance as far as the airplane goes is like a wind gust. You're flying along, you've felt those if you've been in an airplane, right? There's a sudden wind that blows from a different direction. And so we analyze what happens if the wind comes in from a different direction. So we're flying along in this equilibrium, and then suddenly we get a wind gust like that. Notice that the wind gust is from below because I've tilted the velocity vector down. So what does that do? It increases the angle of attack of the wing, because here we were like this, and now suddenly we've got that much more angle of attack. We call this a delta alpha. And we know that for the wings, if they're not stalled, that the lift will increase. You increase the angle of attack on an airfoil, the lift goes up. Here we've got a gust coming from below, adding to that velocity vector, and so the lift increases. So what happens? Here we had the lift with no gust, but now we've got more lift. So we've still got the same pitching moment, but now it's got that extra, and that's not going to be zero. And in fact, the way, since it increases, and since the CG is behind the center of lift, the nose is going to pitch up. Does everybody see that? So we're flying along, everything's balanced. Suddenly the gust comes along, the lift increases. That moment stays the same because remember that moment is constant with angle of attack by definition about the aerodynamic center. And so suddenly now we have a nose up pitching moment. In fact, this is greater than zero. Nose up. So what's going to happen to the angle of attack? It's going to go up some more, right? So it goes up some more, and then the lift goes up some more. Angle of attack goes up some more, lift goes up some more, and it keeps pitching nose up, and the airplane flips. And this really will happen if you have an airplane that isn't balanced in pitch properly and doesn't have pitch stability. So next time, we're going to add a tail because this wing-only airplane obviously is not pitch stable. Because in this case, a force or a moment, in fact, this is a moment, is generated to actually move it away from the initial equilibrium. So if we add a tail, I'll show you why that actually fixes it and it makes it go the other way. So we'll do that next time because you guys need to meet in your groups. So everybody gather in your groups. I think we did 1 over here, 2 over there, and 3 in the back, right? Yeah? Or are you just holding up 3? Great. All right.